yeah, with me, I'll have Daniel joining me, and we'll go through the an assortment of exam questions, and yeah.
Cool. Sorry, where are we up to? I wasn't paying attention.
Yeah. Hi, Daniel. Hey.
Hello.
And live stream, and welcome, and yeah, this should be fun.
Should be fun indeed. All right. So, Thomas, you're up first.
Cool. Okay. So yeah, I think this was from 2015. I forget which semester, but the very first question starts like this. So most of these questions will be very easy to begin with, and this one is too. So it's about a set, and we have to first find the elements of the power set and write down how many there are. So the power set is the set of all the subsets of S. So we've got the power set here of S, and we just have to list all the subsets of S, which in this case is not very many. We've always got the empty set. So here we go, the empty set. And we always have the set itself. So over here we could write it. And then we just have to figure out what the other subsets are. And in this case there are only two. They're the singleton sets, the set containing 1 and the set containing 2. And there you go, your very first mark. Well, okay, half mark, because we did actually have to count them as well. So 1, 2, 3, 4. So that's rather easy. There are 4 subsets here. And that's also equal to 2 to the power of the number of the elements in the set. So if we had a bigger set containing, a billion elements in the set, then it would be 2 to the power of a billion, because every subset we can choose by saying, is this element in it or not? And we can choose, we can ask every element that. So it's 2 to the power of the number of things in the set. Cool. List the elements of this. So here we're looking at the subsets of this that have exactly one element. So this is again rather easy. So let's write A here and B there. These are just the singleton sets, the sets that contain exactly one element. And we're done. Another mark. This is easy. Cool. List the elements of S cross S. So this is the Cartesian product. So here we go. We have S cross S. That's the set of all the pairs. So something something comma something, where the somethings come from S in both cases. So we have, let's just list them. The elements of this, which is what we've got 1, and we can choose 1, and then we can choose 1, 2, and 2 and 1, and 2 and 2, and there we have them all. And all it really says is that we've got a little coordinate system. So if we want to draw a little coordinate system here, we've got S here and S there. S just has 1 and 2 as its little elements, as its little coordinates. And here are the 4 little elements of this crossed product, or the Cartesian product. So for instance, this one here is 2, 1, and so forth. So that's how you can think of it. Okay. List sets of orders pairs all functions from S to S and which are surjective. So that's slightly unusual. The first 3 were super easy. This one you might have to think just a little bit, but it's also easy. So sets of ordered pairs of all functions. So here we're talking about a function. So let's look at the first function. So it sends 1 into something, and we can choose whatever. Let's say 1. We're going to list them all, so we'll come. We could have chosen 2, and we will sort of later. And 2 is sent into something. Let's say 1 as well. So that would be 1, 2, and they both get sent into 1. And over here, we can do the same just by changing those 2 values there. So 1 and 1, 2 and 2 now. And the third function could be, well, now we have to choose something different. 1 and 2, and 2 and 1. And finally, if 4, just to call them something, 1, 2, and and 2, 2. So we can't really do much more here. And if we very quickly draw them, so 1, 2, 1, 2, 1, 2, 1, 2, and you now it's getting a bit messy because I'm doing it quickly, but let's see. Here we've got 1, 2, 2, 1, and 2, 2. And from the little diagrams you can see, here are the ones that are surjective. So this is surjective, and this is surjective. And how did I see this? Well, it's that the image, or the function values that we're hitting, are both 1 and 2. So here we're only hitting 1, so that's not surjective. Here we've got both, and here we've got both. So those two are surjective, and this one is not surjective. And that's the answer to that. And yeah, we're done. We're finished with the very first part of question 1. Over to you, Dan.
Thank you. So something we've done here is just selected questions that we wanted to cover from the exam, 2015 exam, semester 2 last year. So we're going to skip question 2 and move on to question 3, and then skip 4 and move on to 5. So I'll do these next 2 questions for you.
Cool.
Crash. Right, build that back.
Extra drama and action.
Right. Sorry about that, everybody. Question 3. Prove that a function which has an inverse must be injective. Okay. So remember the definition of injective is and knowing, first of all, recall the definition of injective. It says that if you have f of x equal to f of y, then x must be equal to y. And this is a really good place to start when you're asked a question about injective functions. Just remember what the definition is and fill in the rest in between. So, if f of x equals to f of y, somehow I'm supposed to conclude that x is equal to y. Because f inverse exists, because this function exists, I can apply it to this equation, and I can say that f inverse of f of x, well, that's going to be equal to f inverse of f of y, because f of x is f of y. So f inverse must do the same thing to both things, and this here, well, this is just x. And this here, this is just y. So there's not too much to this question. You just need to know what the definition of injective is, and use f inverse to conclude that x is equal to y. Good. Easy question. Next part. Use the Euclidean algorithm to find a GCD. And hence or otherwise do some stuff about finding an x and a y that makes this work. And then even more stuff below that. But I'm just going to quickly read this question to survey the details and see what I actually need here. I need to use not just the regular Euclidean algorithm, but the extended Euclidean algorithm, because I want to find some x's and y's. So I'm just going to keep that in mind. To find the GCD of these two things, I just start like this. So this is part A. 2, 3, 1. That's equal to some multiple of 30. 7 times 30. Which is 210 plus 21. So 30 then is equal to, what is that, 21 times 1 plus 9. 21 is equal to 9 times 2 plus 3, 9 is equal to 3 times 3 plus 0. Good. And at this point I can stop. Well, in fact, I like to cross out this last line and just put a circle around that thing. So whenever you have a remainder of 0, you stop, ignore that line, go back. Here's your GCD, right here. So for part A, I'll say that the GCD of 2, 3, 1, and 30 is equal to 3. Okay. For part B, I need to go find some x's and y's. So now I'll use the extended Euclidean algorithm. First of all, I'll express 3 as a combination of 2, 3, 1, and 30. So I'll start off with my, this is part B now, 3. 3 is equal to 21 minus 2 times 9. And what I'm going to do is slowly reverse these steps. I'll now use, so I first of all use this line. I'll now use this line to eliminate the 9. So this is 21 minus 2 times 30 minus 21, which I can write as 21 minus, plus 2 times 21, so 3 times 21 minus 2 times 30. And now I can use this first step up here to eliminate the 21. And I get this is equal to 3 times 2, 3, 1 minus 7 times 30 minus 2 times 30, which is equal to 3 times 2, 3, 1, and negative 21 minus 2, which is negative 23 times 30. Right, so I'll write this out one more time, kind of in this form, where I've got negative 23, maybe I'll write it like this, 30 times negative 23 plus 2, 3, 1 times 3 is equal to 3, which is almost what we were asked to get over here, except I had a 6 over here, so I'll just multiply everything by 2. And I'll get 30 times negative 46. I'll make that into a minus, because that's what they like. 2, 3, 1 times negative 6 is equal to 6. Hence, I found my x and y, which are integers. So x is equal to negative 46, and y is negative 6. I found my x and y, which are integers that make this work. And it's purely algorithmic. You just apply the extended Euclidean algorithm to find these numbers, and then I had to multiply it by 2 to get the 6. But anything that is a multiple of the GCD would have worked here. Right. Part C. Thomas, did you want to say anything about this before I wrap it off?
No. All looks great. And I think even correct.
Oh, lovely. Do I want any of this stuff? Maybe I'll just leave the part. Maybe I'll leave part B, just in case. Okay, now we need the number of solutions to these equations. So for part C, I might first of all solve this. So this is C alpha. I'm going to solve this equation as an equation with the smallest possible modulus. So notice that 3 divides all these things. So I might say, first of all, that since 10x is equal to 2 mod 77, which is just 231 divided by 3, has It has one solution, essentially. It has x is equal to just whatever x I had before. So where was my x from before? This one, negative 23. Divided by 3. Yeah. Hang on a second. As yeah, the solution to that is just x equals to negative 23. You don't need to say explicitly what the solutions are, but I want to say what the solutions are just to emphasize something. So negative 23 plus 77, and negative 23 plus 2 times 77, and I could even go further, negative 23 plus 3 times 77, and so on. It's got all these solutions, but in mod 77 there is only one solution. The point is I'm going to multiply this thing by 3 and I'll pick up some additional solutions. 30x equals 6 mod 231 has, so that's one solution. Has 3 solutions that are 23, negative 23 plus 77, and negative 23 plus 2 times 77. This equation has 3 solutions. These solutions are all the same in the previous, so maybe I'll put an equal sign there to emphasize the fact that in mod 77 these solutions are all the same solution. But when I multiply the modulus by everything by 3, then these 3 solutions are now distinct. So I have 3 distinct solutions. Mod 77. You could have just said 3, but I wanted to go a bit further. For part beta, how many solutions are there to this? Well, this isn't a multiple of the GCD. So you can just say 0, or you could say that since, or if 30x minus 231y is equal to 7, then 3 divides the left-hand side, but 3 does not divide the right 7, which is the right-hand side. So there are no solutions in this case. And again, you could have just said 3 and 1 and 3 and 0, and that would have been fine, but I think a little bit more detail is nice. Good. Thomas.
Cool. Yeah. So, do we take questions down?
Yeah, do you want to rub it off and I'll take the questions down?
Perfect. Get a bit of work out here. Ooh, that's one was sort of interesting and funny. Like so. Good. Hello again. So we're on to question 2. Let's go quickly. The very first one here has a lot of text, so give an example of a relation on a set 1 and 2, which is both symmetric and antisymmetric. It's sufficient to draw an arrow diagram. Okay, so let's do that. So we have 2, 2 here, and an arrow diagram. So we need 2 dots, 1 and 2 to represent 1 and 2. Now, if there were an arc going, or an arrow going from 1 to 2, because it's symmetric, there'd also have to be one going this way. But it's anti-symmetric, so we can't have that. In fact, that means that we can't have any arcs going from one of the dots to another dot. So, ta-da, there is a solution. If you wanted to draw some more things, if you thought that that was a little too simple, it's perfectly fine as a solution. But, you know, preference, you might have a different, you know, you want it, sorry, you might want a different solution. And there are 4 different solutions. You can add a little loop there, for instance, or one there, or mix and match as you want. So 2 squared is 4 different solutions, all of them correct. And that's it. That's how simple it is. Cool. And
easy. All right. Thank you. Very nice. So for part 3, you're given some partial order on these numbers, and the partial order is division. Draw a Hasse diagram for this thing. Lovely. So 1 will go right down the bottom because 1 divides everything. And I might put 2, 3, and 5 as the next ones. So 2, 3, and 5. I might put them like this. 2, 5, and 3. And I'll join them with colour. So 1 can go, 1 goes there, to 5, and to 2. And maybe I'll just put a little mark on these on the board just to remind myself which ones of these things I've actually put on the diagram. 15 can go up here. Because that's going to go between 5 and 3. I've also got 20 and 30. 20 can go up here. And 30 can go up here. So 20, like that. 15 goes from there to there. And 2 goes like that and that. So notice that I don't need to connect 5 to 30 because that's already connected through the 15. So I'll just tick those ones off. I've got 15, 20, and 30. The next ones are 45 and 90. So 45 can go over here. And 90 can go up here. Because 15 is 3 times, well, 45 is 3 times 15, but those two aren't related, and those two are related. So, there you have it, and I'll just tick those off. I like ticking them off so you make sure you don't miss anything. That's all there is. That's all there is to the question. Just draw a nice diagram. Good, these are easy questions.
Yeah.
Your one might be a bit harder, actually. I'll just take this part off.
Cool.
And
I like the way that you ticked the numbers off because these are super easy, but the hardest bit about them is remembering to get all the elements and draw all the lines. But if you just double check it, this is very easy and should be easy points to or marks. Cool.
There's a question. So there's a diagram with this one and here's a question.
So we actually have to think just a tiny bit.
Yeah. Well, you can't just get away with drawing a picture for this one.
No. But thinking on occasion is fun. Let's see whether we can have some fun thinking. Unfortunately, yeah, these are lovely too, and easy, almost free points if you know what you're doing. Unfortunately, sometimes you have to write a tiny little essay, but luckily you don't have to be very precise. It's just as long as the markers know what you're talking about. And let's see what I'm talking about right now. So we've got 4 questions. They all relate to this graph here. And by the way, the first 2 lines, that was about the previous question, not this one here. We're looking at this graph here. And we have to figure out whether it's bipartite, planar, has an Euler circuit, or a Hamilton graph. And in each of those 4 sub-questions, we have to give some reasons for our answer. The answer is going to be either yes or no in each case. So we have to figure out first for each of these things, is it bipartite or is it not, and so forth. And then we have to, after our good guess, give some answer that, or give some reason that validates that. So let's begin. Is it bipartite? Well, here you could just start by drawing it up, start with one vertex and try to draw a bipartite graph up. That's one way of doing it. But you can also have a shortcut here because the graph isn't very complicated, so you can quickly check, does it have a cycle of odd length? And yes, it does. Look here. So A, B, F, E, C, A. That's a cycle of length 5. So if you wanted to draw this graph in a bipartite way, you'd also be drawing that cycle in a bipartite way, but you can't because it's got odd length. So that's the first answer. So A, is it bipartite? No. Give reasons, is it bipartite? No. G, well, maybe we should write it out. So G is, let's use another colour, not angry red, not bipartite. And then we have to have some reason. Since G contains a cycle of length, or of odd length, maybe is better. There we go, of odd length. And if you wanted to be more specific, you could even say which cycle you're thinking about. A, B, F, E, C, A. And that's a perfectly good answer. Cool. What about planar? Is this planar? Well, sure it is. You can almost see it. So here the answer is yes. G is planar. Because we can redraw it in a planar way. For instance, like this. There we go. And a couple of edges between these vertices. There we go. And all we've done here is pull the G into the middle. So just to make sure that everyone knows what we're doing here, especially the marker. Let's draw the vertex G there and write G there, and B, F, etc. C and E. Cool. Done. Third thing, does it have an Euler circuit? And at a glance, of course it does. And why is that? Well, I'm not even going to think of an Euler circuit. I'm just looking at the vertex degrees, and they're all even. And we know if all the vertex degrees are even, then it has an Euler circuit. So that's what we can write. G has an Euler circuit. Go down here to avoid writing on this picture. Since each vertex degree is even. So here we see it's 2, 2, 2, 2, 2, 4, and 4. So they're all even. Finally, does G have a Hamilton or Hamiltonian path? And that's the only tricky one. It's not very difficult, but it's a little bit fiddly to write down. So let's do that. So here we've got D. And my claim is that it doesn't. And how do you see that immediately? Well, you might be able to see it if you sort of try to draw a Hamilton path. You'll always clash in either B or C, the two vertices there. But why? Well, here's one reason. If you have a Hamilton path, it has to go to every single vertex. Go to it and then leave it again. So that means in all the vertices that have degree 2, it'll be going along each of those edges that connect or that are incident to the vertex. So in this case, it'll have to contain both of these edges, because that's got degree 2, these edges. In fact, all the edges would have to be in the Hamiltonian path. But you see that then we'd have here or there a clash where we have to go into C and B at least twice. So we can't have that. How do you say that? How do you write it down sort of relatively compactly? Well, there's no real good way, but let's try. So G has, and let's use an angry red pen again. no. That's somehow satisfying. I'm not quite sure why. G has no. Whoops, Hamilton is with a capital H. Let's respect the name. Hamiltonian path. Since such path would need to contain all edges. It is a bit of an essay here. Incident with vertices of degree 2. I'm falling asleep myself, and the marker might too, but let's continue bravely. There's one little niggle here. It would have been easier if they'd written cycle in this question here, because then what I just said would be strictly true. There's one tiny detail which I haven't mentioned, is that because we've got a path, we can technically skip one of the edges, but we do have two of those vertices where we will have a clash. So at least one of these vertices will be visited twice. So we can say of degree twice, except one edge. That is all but one of the edges. And then just to, now the marker knows what you're trying to say, then you can sort of be let off the hook a little bit by cutting it short and saying, which is not possible, and raise your finger and look assertive, and unfortunately the marker can't see that, but there you go, which is not possible. And there we go. I feel like writing the end of the proof there just because it seemed like a big thing, but there we go. That was the only slightly annoying part. The rest is nice and easy, and it is in general. So there we go. Cool. What's next?
Question 3.
Question 3. Cool.
Giving another very wordy question. But good lifestyle advice as well.
It is. Pay your bills and hope that your ISP isn't incompetent. You can control the one, the other. Live with, suffer under with grace. Let's see. So, here we have a topic 3 question, in question 3, and it's about something. Well, if I pay my bill, well, okay, there's a lot of text. So what we have to do here is break this text down into what it actually says, into propositions, and write those propositions in symbolic form, and then we've got some statements that apparently conclude that something is true, something else is true, and we have to show that flow of logic is actually valid. So let's do that. So first of all, we need to define some propositions. So first of all, we have, if I pay my bill on time, okay, I pay my bill on time. That's the first thing that we could look at. So let's see, P, for instance, that could be, I pay my bill on time. and my surface is cancelled. Okay, so let's see, surface. My surface is cancelled. What terrible fate. Then something. My ISP is incompetent. That does not surprise. My ISP is incompetent. Some might say that this is a tautology. This is always true, but that's not necessarily the case here. So, what does it say? Okay, so here we've got the three propositions that we're talking about. Now, there are some statements here. So, if something and something, then something. And the second statement is this, but, and here but means and then therefore I didn't, etc. So let's try to break that down into seeing what they're saying. So, if I pay my bill on time, that was the first one, P. And something else, that was the second one. So here we have and. So if these two things are true, then, so we have an arrow there, the then arrow, my ISP is incompetent, which is the I. Now, actually, I might just write that again, because in a second I'll be using contraposition, which I might have over here. So let's just write a 1 there. So we had P and S implies I. And before we go on, I'll just turn this around by contraposition, because we'll need that later. So if this is true, then this is true, which is the same thing as saying, well, if that's not true, then that can't have been true. So not I implies not P and S, which is the same thing as not P or not S by De Morgan's law. Cool. My ISP is competent. Okay, that's nice. So that's the negative of the statement, which says my ISP is incompetent, so this is competent. Got to keep track of what's what. So this is not I, not incompetent. And, so that's the but there. And my service was cancelled. Oh, that's annoying. Okay, so these two statements are what we assume, and then we conclude, therefore something. So let's do that. So therefore I didn't pay my bill on time. So that was not P. Okay, so this was part A, and this is now going to be part B, where we show that this statement here is logically valid. Okay, what can we do? Well, we can start off with number 2. Well, 2 implies that, well, we've got that both this is true and this is true. In particular, that this is true. So not I, so the ISP is not incompetent. Now we can use number 1, because we have that if not I is true, then we have this going on. In particular, we've got not P, or we've got not S. Okay, now we can use 2 again. 2 says that both of these are true. In particular, we've got that S is true, so we've got 2 implies that S. Now, if you combine these two statements here, we've got S is true, and then either not P or not S. Well, if S is true, then this is not true, so this must be true, not P, and that's what we wanted. Done. Awesome. So we had to prove something, end of proof, and if I wanted to be really fancy, I could write proof here. It's a bit messy, but there you go. And we're done. So that's all we needed to do. That wasn't too hard, even though there's a lot of text and writing to do. Cool. Alright, so.
We're up for a bonus question now. The chat's asked for a Kuratowski theorem question from 2013. So
awesome. Cool.
I'll just put that on the board.
Yeah, awesome. Yeah, there's the... Yeah, those Kuratowski questions, they're fun. Yeah, not always not always straightforward.
So here's an aside to 2013 semester 1. Question 2, part 3C.
I'm reckoning it might be good for us both to have a look at this. Partly because it's fun, partly because you need to be able to see some trick, or not trick, but some way forward.
Cool. Good. So is the graph planar? Of course, if it was planar, you could just draw it and it'll be planar and that's considered good. Proving a graph is not planar requires you to use Kuratowski's theorem, which means somehow in this graph is contained either K5 or K33.
So one thing that you can start off doing is see, well, if you wanted to end up with K5, then the vertex degree will be 4 for each of the vertices when you end up with K5. But the operations that we were allowed to use, like subdivision, for instance, make those two edges into one by sort of smudging out the A. That can only, well, that won't change the vertex degree of these. The other operation that we're allowed is to cancel edges, and that can lower the degrees, but it can't. So the operations we've got can't raise them. And here you see that we've got all of the vertex degrees being 3 or less. So we won't be able to get K5 from this picture. So if we are to use Kuratowski's theorem, we're supposed to head for K33. And the first thing that we could do is use subdivision on A, so that we just have one line there. Mm-hmm. And a little, if you're sort of wondering how to get to K33 or K5, try to keep in mind the vertex degrees. That's a good way of, well, it helps you a little bit. Still a puzzle though. It's a nice one.
Oh, there we go. Thank you. Teamwork.
Yay. Awesome. Pretty. Cool.
There we go.
So at this
do
point,
you write something there, Thomas, to indicate that A was smudged out? How do you like to write that?
Yeah. Like this.
And maybe A, B, E becomes B, E, something like that.
Yeah, sounds great. Yeah. A was smudged out.
Yeah. So B, A, E becomes B, E.
Yeah, perfect. And how many vertices do we have now? We've got 6. Awesome, because if we want K33, then we need exactly 6 vertices. So we can't delete any vertices by subdivision. So either we've got K33 here, or we need to get rid of some edges. The vertex degrees here are all 3. So in fact, I'm guessing that actually is K33 and we're done, which is a bit of a relief because, sometimes it's a bit tricky using this proposition, this Kuratowski's theorem, and you don't want to spend too much time in the exam doing this. So, awesome.
And B is connected to all of those. BE, BG.
Perfect.
G. And BC. C, sorry.
Cool.
And C is connected to, well, let's do the next one. D is connected to C, G, and F. So D is also connected to everything, and F is connected to C, D, and sorry, C, E, and G. Good.
Beautiful.
As F.
Awesome.
Good. And we'll put an arrow there. And this is nice because it really drives home. I mean, this is already K33, but now we're being really explicit about this thing being homeomorphic to K33.
And this is worth a bit of excitement.
Yeah.
There we go.
Good. So I like what you said there, Thomas, about just looking at the number of edges you've got and realizing that you'll never get this into K5.
Yeah.
Another thing that will give you some information about which edges to kind of combine and smudge, which vertices to smudge out, is you need to eliminate the odd cycles. And this A here is giving you this odd cycle. So you've really got lots of reasons to think this is the edge I'm going to smudge it. Oh, this is the vertex I'm going to smudge out.
Yeah, nice. Yeah, and I suppose at some point one should write up by Kuratowski's theorem, etc., etc. This is not planar. Should we do that or?
No, I think we'll just say that.
Perfect. Cool.
We can do that because we're on video. I mean, if someone wrote this in the exam, do you think they'd be marked down for not mentioning Kuratowski's theorem?
They should write Kuratowski's theorem, but if I were doing the marking, I wouldn't mark them down. But I might not be doing the marking of that particular one, so it depends a bit on the marking.
Yeah, play it safe and
Yeah.
make sure you write down the name of the theorem.
Yeah. Cool. What's up next?
The cumulative sequences one.
Perfect.
So back to 2015. I'll just grab that.
Ah, thank you. By the way, do you remember, in fact, I have the answer right here. Someone's just asking whether it's possible to, okay. So the question was, are you allowed to draw with pencil and stuff?
Mm-hmm.
All answers must be written in ink, except where they expressly required pencils may only be used for drawing, sketching or graphical work. Okay, so it sounds as if you're allowed to draw in pencil. Yeah, cool.
Yeah, sounds fine. Bring a pencil.
Yeah. Okay.
So here we have the definition of cumulative sequence. The first part is really just to write the negation of this statement, which is fairly straightforward. So for question B, part A, write down the negation of this statement. All the exists flip to for alls, and all the alls flip to exists, and then you have to negate this statement here. So the negation of the statement is for all m greater than or equal to 2, there exists some n bigger than m such that Sn is not a subset of S2 union. So fairly straightforward. You just turn to each of these things, flipping the exists to alls and the alls to exists, and you have to negate that in some other way because it doesn't have an all or exist in it. So part A, write the negation of statement. Part B, prove that this is not a cumulative sequence. Good, so we're going to use part A here. Let's see. B. For all m greater than 2, so we need to prove something for every m. So let's just say for any m greater than or equal to 2, I need to produce some n. It's not clear what n I want just yet, but I'll need to produce it. So I'm going to say let n equal, and maybe I don't know what it is yet, but I'll fill that in just a moment. Then Sn has to not be a subset of the others. So Sn has to be not in S2 union S3 union Sn. Now let's think about what this means. These are the multiples of 2, the multiples of 3, all the way up to the multiples of n. So I've covered a lot of ground here. This union is quite large. It covers all the multiples of integers from 2 to m. What's not going to be in here is any prime bigger than m. So if I let n be the next prime bigger than m, so I just select whatever prime comes next after m, then this won't be in here because n is an element of Sn, but n is not an element of S2 union. So it requires a bit of a leap of faith here. You know what you need to prove. The best way to prove something exists is to actually tell the person who's reading your stuff what it is. So here, front and center is my n, which must exist because there's always some prime bigger than n, and it has the desired property that this object here is not properly, or not contained within this set. So, there you have it. Thomas, any comments about that?
No, that was beautifully done. I hope that all the people at the exam, they do it as beautifully.
Well, hopefully they get exactly this question. Cool. All right, question 4 now.
Let's go. That one. That's
the box one.
Yeah, I like that one. Actually,
Yeah. Do you leave that up?
yeah, I don't actually think I need to.
I'll take it down, otherwise it gets confusing.
Yeah, cool. Sort of go. Cool. Yeah,
Thanks,
so, question 4. That's so here we have topic 4 type question. How many ways of whatever? I love these type of questions, and I hope that after the possible initial shock of having to learn it, that you're getting to love it too. It's a pity that you have to actually mix exam stress in with this beautiful stuff, but let's have a look at it. How many ways are there to place 9 different letters, like these here, into a 3x3 grid, just like you see here, such that each row and each column contain a vowel and 2 consonants? So, okay, let's quickly just think what they mean there. It just means that we're putting the vowels in positions like this, where you don't have any vowel being in the same row or column as the others. So how many ways can you place the vowels like that? Well, for the first vowel in the top row, we could have placed it in any of the 3 columns, and then once you've done that, for instance, if you've placed it there, we can't place the second vowel in that column, so we've got 2 choices, and so that locks down the 3rd choice. So all in all, we have 3 factorial ways of placing the vowels. So let's write that up. So there are 3 factorial, or 6 ways to place vowels. And so, in fact, we could even write them up. We could have vowel, 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 and so forth until we have vowel, vowel, vowel. Cool. So we've got 6 ways to place the vowels and the consonants in that sort of pattern, but we haven't chosen which vowels and which consonants yet, so let's also do that. So we've got how many vowels? Well, we've got 5 different vowels. So for each of these positions, vowel, 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 we have to place a vowel, and we've got 5 choices. So we've got 5 to the power of 3, vowel.
They have to be different vowels.
Do they have to be different? Ah, thank you. Different letters, thanks. So we have to choose, out of the 5, we've got 5, and then for the next choice, we've got 4. For the third choice, we've got only 3 left. So that's 5, 5,3, the number of permutations there. Thanks. And the same thing is true for the consonants. There we've got 6 consonants that we need to choose, and they all have to be different. They're not going to be vowels, so we don't have to worry about the vowels messing up the counting. So it's rather clear cut. We've got 21 consonants, 26 minus the vowels, so 21. And here we're choosing, well, 9 minus the 3 vowels, which is 6. There we go. So consonant choices, and then all of these 3 things that we've counted are independent of each other, so we can just multiply them together to get, well, my hand does do the job here, but this might be better. In total, 3 factorial times p 5 3 times p 21 6, and that is your answer. Now, you might be tempted to work out that number, what it actually is, and I'd suggest not doing that, because if you've got it in this form, then the person marking can actually see what you're thinking. The number itself won't, well, if it's the correct number, then you'll of course get full marks, but if you make some little error, the marker can't give you partial marks as easily as if they see an expression like that. Anyway, yeah. And over to you.
Cool. Thank you. I'll just grab that.
Oh, thanks.
Yeah, I definitely would recommend writing it out in this way so the marker can see what logic it is that you're following, because people will follow different paths to what is hopefully the same answer, so it's nice to see what that path is. The final question of the stream is this question here, number 5, pigeonhole principle question. Consider a square with sides of length 12. Prove that you've got 145 points somewhere in the square, and 2 of them must be separated by, at most, √2 units. So at least 2 of these things are close. Now the issue with all your pigeonhole principle questions is how to construct the holes. So you've got all these dots, but how are you going to make the holes? I'm going to draw a diagram for this. In fact, diagram helps no matter what the pigeonhole principle question is that you have in hand. So here's my square. I'm just going to like that. I'm just going to make some lines to indicate that I'm making boxes of, well, squares actually, of side length 1. So this is part A. Good. There are 144 such boxes, and I have 145 points or pigeons. I like to remind myself how this is going, so I like to say there are 145 points, and these are going to be my pigeons. And 12 squared equals 144 boxes, which are my holes. So this is just the statement of the pigeonhole principle. Here I've defined my pigeons, here I've defined my holes. By the pigeonhole principle, there is at least one box, or hole, containing at least this many points. And this number here is 2. So there is at least one 1 by 1 square that contains 2 points somewhere like that, and they have to be less than root 2. So it's 1, that's root 2. They have to be at most root 2 apart. Good. And that's your pigeonhole principle question. Part B is almost identical, except you have to redefine your boxes. So I'll just do part B, and I'll leave most of this up, and I'll just redefine my boxes like that. I've got substantially less pigeons going in here. That's going to be different. Okay. So this is part B, and I'll do part B in blue. B. Subdivide, so it's the same question, except the numbers are different. Prove that if there are 13 points given in the square, 2 of the points are separated by at most 5 units. Okay. I'm going to subdivide my square, but now I'm going to subdivide it differently, and this is the challenging part of the question. How do you construct your boxes? I'm going to make the boxes of size 3 by 4. 3 by 4. Because this is length 12, I can do this like so. So here's, that's supposed to be 4 and 4, and like that. And that's not, there we go, 3, 3, 3. That's what it's supposed to look like. So I'm dividing my square into boxes of size 3 by 4. I don't really want to describe how I'm doing that in words, so I'll draw a picture. The picture is horrendously not to scale, but that doesn't matter. It's a math subject. There, I can get away with some lack of artistic skill. So subdivide the square into boxes of this size. There are, well, I know exactly how many points there are. There are 13 points. And how many boxes have I got? 12 boxes. That's 3 times 4 is 12 boxes. Good. I've got slightly less boxes than holes. That means the pigeonhole principle is going to tell me something important. Therefore, by the pigeonhole principle, at least one of these boxes must contain at least 13 divided by 12, which is again 2 points. And here, if I draw my triangle, that's I've written it slightly differently. That's a 4, that's a 3, and that's a 5. Therefore, these points are separated by at most 5 units. Cool. That's beautiful.
Yeah, no, I don't really have anything else to add, except that, as you said, if you look at the numbers, they often give you a bit of a hint as to what you should do. Like here, the 5 sort of comes out of the blue in some ways, but in other ways, if you look at 12 and sort of think that we're dealing with boxes and possibly something diagonal. Ah, Pythagoras. Ah, cool. 3 and 4. Okay. So it's not always straightforward, but given the numbers, it's not too bad, especially because you've got tutorial problems and past exam papers, which sort of push you in that direction as well. Yeah. So.
But I just recommend drawing a picture. When you get thrown a pigeonhole principle question, draw a picture to help you organise your thoughts and these numbers into some kind of logical way. And then and using the picture, you'll hopefully be able to define your boxes. And once you've got the boxes, it just falls out.
Most of the time, if you have, for instance, 13 points, so obviously your pigeons, then you're looking for something to do with 12. Once on rare occasion, you get something that might not be the number just below it, which is a bit evil and nasty, but almost always you'll have the number below it, like if it's a billion, then it'll be a billion minus 1, and that number you can sort of see, oh, okay, it's got to do with 12 boxes here, for instance, or whatever. So, yeah.
Cool, well, cool. That's the end of the stream.
Yeah, well, thank you very much.
Yes,
this was actually fun.
And good luck in your final exam.
Yeah.